charge of designing the mount system. Mount systems are usually used to treat sewage or gray water, but in this case, we're just going to collect all the gray water from the facility, filter it through the mount system, and transport it to irrigate a bamboo field. So I got my calculation data and equations from a manual specifically used to create sand mounts. And from the field survey data, we calculated that around 460 gallons per day are needed from the facility, but we only assumed 80% of that was going to get captured. So I dimensioned the mount to handle a flow of about 383 gallons per day. From our visit, we saw that the land was relatively flat, so I used a 0% slope in the design. So here's a cross-section of the mount system. First, the water we pumped into these perforated pipes that are embedded in the gravel bed. The water then trickled down through the sandy loam, hit the clay, which is sort of impervious, so it will cause the water to go down to the middle and be collected by this pipe that through gravity will transport the water to a bamboo tube. So here's the overall plan view and dimensions of the entire mount system. This system is run under pressure, so the minimum velocity in the pipes need to be at least 2 feet per second, and the force main will deliver 4 doses of 96 gallons per day. So here's some of the details of the laterals inside the bed. They each will have 4 perforations spaced 3 feet apart, and the connection between the manifold and the lateral is a reducing coupler, and the reason for that is to reduce this.
So now we will be talking about our third component, which is the anaerobic biodigester. With the opportunity we were given to travel to Nicaragua, we were able to identify 2 issues that our biodigester would address. The first issue is deforestation. Because of deforestation, the community of Sabana Grande faces issues such as excessive runoff and surface water contamination. Another reason for deforestation can be due to the fact that women use wood to cook. The second issue pertains to the respiratory health of these women, who cook with the wood in these very small kitchens that don't have proper ventilation. Because of the improper ventilation going on inside the kitchen, the women are prone to getting ill because particulates enter their lungs and their blood loses the capacity to deliver oxygen efficiently to the rest of the body.
So in looking for a solution to these problems, we considered a technology already in use at the Solar Center in El Proyecto. We are considering biodigesters. There are many different types of biodigesters, as you can see here, but they all essentially work in the same way. They take in organic material mixed with water to go through and digest, where the bacteria inside of the digester heat further breaks down this material and creates a biogas. This biogas is often high in methane content and can be used for cooking. So a biodigester captures that gas and uses it as a fuel source. The effluent from the biodigester, that's the fluid that moves through it, can also be used as a fertilizer for plants and other crops that might be in the area. Our design strategy was to design a biodigester that was affordable, durable, easy to construct with the materials available, and easy to operate and maintain.
The design criteria that we used as the basis of our design was that our biodigester is to be located relatively close to the volunteer kitchen, where it will then be connected to a cooktop. After looking into typical types of food that the community from Nicaragua consumes, we decided to produce 6 hours of cook time from our biodigester and about 95 cubic feet of biogas yield for just 1 burner. In designing our biodigester, we also had to take into account that our input source is only going to be cow manure because it is the easiest to get a hold of in the area, and its effluent is rich in nutrients that are suitable for both food and the reforestation project that is currently going on in the community.
Considering all of these factors, we decided to go with a more generic plug-go biodigester. Our design includes a reinforced concrete base covered by a polyethylene sheet, which is essentially a plastic sheet that covers the concrete to capture the gas. A PVC pipe will be welded to the top of this sheet and will run all the way to the kitchen where the gas can be used for cooking. Our total volume of our biodigester is approximately 200 cubic feet, and that includes the space for the gas. And now Hilda will go over some of the other details of our design.
So in order to ensure that our biodigester works efficiently, we need to make sure that only the slurry gets in. For this reason, we have provided concrete enclosures at both the inlet and the outlet structure is relatively fragile because of the polyethylene cover and because of the microbial activity going on inside. For this reason, we decided that we were going to provide a protective structure composed of some wood framing, fencing, and a metal deck to ensure that humans nor animals do damage to the biodigester. Lastly, we decided to use a soda bottle safety valve that will release the excess pressure buildup in the bag. And along with this soda bottle safety valve, we will also include a steel wool that will react with the hydrogen sulfide and eliminate the harsh odors, basically the sewage odor, from the area.
So, in designing our biodigester, we're hoping to make it easy to operate and maintain. There will be daily care needed for our biodigester. For example, 30 gallons of slurry, which is just the cow manure and the water, will have to go into the biodigester daily. We are hoping to achieve approximately an 8% solids content, and I know we probably won't get that type of precision when the biodigester is actually in use, but we want it to be fluid enough to go through the digester without clogging it. The effluent will also have to be removed as the slurry is added because it is a plug flow type digester. So the effluent will be coming out as new material is going in, and this effluent will be contained inside of our enclosure at the outlet. The operator of the biodigester will also have to pay attention to the safety valve that Hilda was talking about. This safety valve releases the gas, so special attention will need to be paid to this valve to ensure that the operator is inputting the appropriate amount of manure into the digester.
Now we're going to get into the project cost. These are estimated values for each component as well as the labor. So for the compost latrine, it's about $900 for each one, and therefore multiplied by 45 homes, about $40,500. The water efficiency system facility is about $23,500, and the biodigester luckily is only $400. And the cost of labor will be approximately $25,500, and this will also include the administration costs. And so our total project cost is a little under $90,000 total.
So now we can discuss some of the non-technical issues. Typically in designing for developing countries, there are many non-technical issues that go along with the design. You must either bear those in mind while designing, or at least take account for. For our design, we have the unique opportunity to not only provide the community's needs, but also directly address these non-technical issues. And in doing so, we feel that we're able to provide projects that improve the overall quality of life in an economic and environmentally conscientious way.
So now we're going to wrap up this presentation. We have designed these components for the community of El Proyecto because it is a community at a crossroads. They are at a point in time where if they do not learn to develop in a more environmentally balanced way, they risk the depletion of all of their valuable natural resources. The people of the community are well aware of this and are highly motivated to move forward into the future in a more sustainable way. We have designed 3 independent components to give the community 3 opportunities to improve and move forward sustainably. By having these components separate of each other, the community can choose to implement them gradually over time or as they can afford them. And hopefully, with each component, they will serve as an example to the other communities around them.
So through working on this project, we've really gained a strong connection with this community, and especially the families that we work with and surveyed and stayed with. So we would like to ask you if you can assist us in any way that we can make this project an actual reality. Please see us after the presentation, and we'd love to hear about your ideas. We also like to thank our external and academic advisors and those who help fund us be able to go to Nicaragua and see what kind of projects they absolutely need. And they took us with welcome arms and let us stay in their homes. And we also like to thank you, the judges, for coming here to help watch our presentation, and we'd like to open the floor for any questions.